Welcome back to Calculus 2, Section 3.3, Trigonometric Substitution. In Section 3.3, we're going to have three topics. Recall back, Section 3.1 was substitution. Substitution was taking an complex-looking integral and revealing that by a substitution, it could be made into an elementary integral. 3.2 was on how to integrate trig integrals. Here in 3.3, we're going to bring those two together with substituting an x, an algebraic x, for a trigonometric constant a times a trig function. We'll look at the substitution with sine, tangent, and secant, determine what are the various situations which determine each trig function, sine, tan, or secant. And the substitution method is going to take an algebraic integrand and turn it into a trigonometric integrand. Let's get started. All right, if we're going to let x be a times sine of theta, we could note that the expression y equals radical a squared minus x squared would result in a semicircle, that for this radicand to be defined, we would need the absolute of x to be less than or equal to a. Another way to express that is that x must fall between negative a and positive a, inclusive of negative a and positive a. Or we could rephrase that, dividing through by a, as x over a must be from negative 1 to 1, inclusive. And this, you'll know, is the range of sine of theta. Good. So in our expression, if we make the identity that x is some positive a times sine of theta, we can easily solve and come up with x over a is sine of theta. And this x over a, you want to recall, is reminiscent of a definition for sine in terms of a right triangle, where the x would be the measure of the opposite and a would be the measure of the hypotenuse. Very good. Now, by placing a restriction on the input on the angles theta from negative pi over 2 to pi over 2, we can come up and we can isolate, we can recover a theta from the expression x over a equals sine theta by applying arcsine to both sides. Okay, so the top line is just a statement in terms of the range of sine. And then if we take a restriction on the thetas, then we can recover the theta by applying arcsine. So it's key to remember that theta lies in the region negative pi over 2 to pi over 2. Very good. So let's do an example. Suppose that we have an integral, capital I, with integrand, a radical function. Now, we're going to have three trig substitutions. The case of trig substitution x equals a sine theta will be based off of a radicand a squared minus x squared. In this case, 4 equaling a squared implies that a is 2. So if we set up x equals a sine of theta, we would set up x equals 2 sine of theta. This is substitution. So compute out the differential dx by taking a derivative with respect to theta of sine of theta to get cosine theta. Therefore, the differential dx is 2 cosine theta d theta. And swap out. So the easy one is the dx. Plug that in. For 2 cosine theta d theta is dx. And then x squared, well, square x, and you get 4 sine squared theta. So 4 sine squared theta is now appearing in the radicand. Good. Okay, let's do some algebra. So look at the radicand. In the radicand, we can factor off of 4 from both terms, and we know that the square of 4 is 2. So factor off the 4, apply the radical to the 4. We're going to get another copy of 2. I've brought the 2 coming from the differential all the way out into the front. It's a constant. And then if you look at the radicand, it simplifies down to 1 minus sine squared theta. And if you think back to Pythagorean identities, you know that this is going to swap out for cosine squared theta. Good. Let's simplify. So for the constant, we get 2 times 2. That turns into 4. Use the Pythagorean identity for the radicand to become cosine squared. And next, we want to simplify the radical term. And the radical never returns a negative value. A radical function is non-negative. However, cosine does produce negative values, so we have to be a little bit careful when evaluating this radical. On the other hand, we know that theta has a restriction. That theta is angles from negative pi over 2 up to pi over 2, which means that cosine is going to be non-negative. And so because cosine is non-negative, this radical of cosine squared can be simplified as just cosine. So that we get cosine times cosine, or integrand cosine squared. Okay, so here is the whole point of the section, is that we began with a radical integrand, which is typically problematic, and we've turned it into a trig integral, i.e. the previous section. So this is wonderful. We can now just apply the techniques that we learned in the previous section. How do we evaluate this trig integral? Good. So that's the meat of this section. Very nice. So let's go ahead. On cosine squared, we can use a power reduction identity. Note that there is a 4 out front. The power reduction identity involves a multiplicative 1/2, so 4 goes down to 2. And then the power 2 essentially turns into a doubling of the parameter theta. And now we have elementary integrals, so that the 1 goes into theta, and cosine of 2 theta goes into 1/2 sine of 2 theta, distribute the 2, and 2 times 1/2 goes to constant 1. Very good. So we have evaluated all integrals. And we're producing something in theta. Yet, we need to go back and look. The original variable was x. So we need to use our substitution identity, x equals a sine theta, to convert thetas back into x's. So x is a sine of theta, and here we're looking at sine of 2 theta. On the theta term, we know that we're going to be able to apply arc sine in order to get theta being arc sine of x over a. But sine of 2 theta, we're going to have to look elsewhere. And we can use a double angle identity on sine of 2 theta. So recall that sine of 2 theta is twice sine of theta product cosine theta. So that's looking good. And 2 sine of theta, that is just x. So now we need to find an expression for cosine of theta. And for that, we can use the Pythagorean identity. So Pythagorean identity, cosine squared equals 1 minus sine squared. Apply the radical on both sides. We can maintain just the positive root as theta is restricted from negative pi over 2 to pi over 2. In other words, cosine is non-negative for those angles. And then to come up with this expression, 4 minus x squared, that's 4 minus x squared would be 4 squared sine squared. We only have 1 minus sine squared, so we need to introduce a 4 on each of these terms. That'll give us 4 minus x squared. But we can only introduce a 4 in the numerator if we also divide by 4. Introduce a 4 in the denominator. And a 4 in the denominator under a radical turns into 2. All right, so our cosine theta term will be this radical over 2. 2 sine of theta is x. 2 theta, solve x equals 2 theta for theta by applying arc sine. So 2 theta becomes 2 arc sine of x over a. 2 theta is x, and the radical over 2 is cosine. Very good. And this has returned our antiderivative in terms of thetas, returned that antiderivative as a function of x. Fantastic. Your turn. Integral I is introducing an x in the denominator to the example that we just did. And integral j is replacing the 4 in a different location. So an algebra challenge. Okay, so note that what we're looking at is a constant minus the variable of integration squared as a radicand is a tip-off to do trigonometric substitution with sine. Good. So that's the first topic. Next, when do we use trigonometric substitution using tangent? Okay. So now look at the radicand. The radicand takes the form of a constant plus the variable squared. The previous using sine was the constant minus the variable squared. Change the difference to a sum, and that's a candidate for using trig substitution with tangent. As you can recall that 1 plus tangent squared of theta is secant squared of theta. Okay. Now, before looking at that specifically, let's think of the radicand. The radicand is a sum of positive terms, since something squared is positive. Thus, no matter what the a is, x squared, we can always add in an x squared for any x. Good. Thus, if we set a x equals a tangent of theta and place a restriction for thetas from negative pi over 2 to pi over 2, then these x's will run from negative infinity to positive infinity. Note, remember that if you think of the graph of tangent, that tangent is asymptotic with x equals negative pi over 2 and x equals pi over 2. In other words, that the outputs run the entire number line. Good. Do an example. All right, we have an integral. There's a radical involved, and the radical is a sum or difference of a constant squared and the variable squared. We did the case of the constant squared minus the variable squared. That was substitution with sine of theta. Here we're looking at a constant squared plus the variable squared. Let's substitute with tangent of theta. So if we let x equal tan theta, compute out the differential dx as secant squared theta d theta, make substitutions, dx numerator becomes secant squared theta d theta. Denominator of the integrand is the radical. Radical is radical. 1 is 1. The plus is the plus. And then x squared turns into tan squared. Good. Pythagorean identity in the radicand takes 1 plus tan squared into secant squared. And then algebra, we'd like to remove that radical. So a lot of the motivation on trigonometric substitution is to get rid of that radical. And the radical of something squared is the absolute of the quantity squared, i.e. radical is gone. So here, remember that we are placing a restriction on thetas, negative pi over 2 to pi over 2. Then you want to think of the graph of secant. Secant over the range of values, negative pi over 2 to pi over 2, is bigger than or equal to 1. In other words, it's positive. And because of that, when evaluating the radical of secant squared, for these thetas, we do not need the absolute value. Nice. Then the integrand simplifies to secant theta. And you had an assignment in the previous section on evaluating the integral of secant. Let's go through it. That the integral of secant is the natural log of the absolute value of the sum of secant of theta plus tangent of theta. Pick up any constant of integration. And now we have the task that our antiderivative is expressed in thetas, but we want to return it back to the dummy variable of integration. Good. So we have that x is tan theta, so that's what we're going to do for tangent of theta, turn it into an x. But then we can use the Pythagorean identity. Secant squared is 1 plus tangent squared. Apply the radical, again because theta has a restricted value, negative pi over 2 to pi over 2, exclusive of endpoints, that secant will be positive valued, thus we can choose the positive root. Beautiful. So plugging this in, tan theta is just x, and secant theta is the radical term. And that's it. Very nice. Very good. So manipulate the previous integrand, add an x squared term in the numerator. See how that affects the trig substitution. On the integral j, hide the radical in the fractional exponent. Notice that's 3 times 1/2, and 1/2 power is the same thing as the radical. Good. So again, we've looked at a constant squared minus the variable squared. That would substitute with sine of theta. And here, this second topic was a constant squared plus the variable squared, meaning substitute with tangent of theta. Excellent. And then the third substitution is to substitute with secant. So there you think back to the Pythagorean identity. And you can take secant squared and subtract 1 to produce tangent squared. Okay, so we started with the constant squared minus the variable squared. That was sine. Then we looked at the sum of two squareds. Now we're looking at the variable squared minus a constant squared. This is a candidate for trig substitution with secant. Good. And again, let's make some notes on the radical term. That now we have the x changing values. For example, if you were to take x equal to 0, that doesn't work because you'd have to do the radical of negative a squared. Thus, x's need to be at least as big as a, or anything bigger. Likewise, x's can be as small as negative a, or anything smaller. In other words, we're forcing the radicand to be non-negative. Good. And then when you look at the graph of secant, that these outputs, x is bigger than or equal to a, that those occur on the graph of a secant, those outputs are produced over inputs theta from 0 to pi over 2, and the outputs of less than negative a occur for inputs on pi over 2 to pi. Okay, nice. So let's look at this integrand. We have a denominator, the variable squared, minus 9, which is 3 squared, raised to the 3/2. Let's identify that a is going to be 3, and set x equal to 3 secant theta. If x is 3 times secant theta, compute out the differential dx. Derivative of secant theta is secant theta tan theta. Tack on the differential d theta. We can then swap out our differential dx for 3 secant theta tan theta d theta. Plug in through the denominator. X squared becomes 9 secant squared theta. And minus 9 is minus 9. Pythagorean theorem is going to allow us, first let's do some algebra. If we take 9 and raise it to the 3/2, that's the square root of 9. 3 to the power 3 gives us 27. And then 3 over 27 is 1/9. Now let's do the Pythagorean theorem in the difference base. Secant squared theta minus 1 is tan squared. And tan squared raised to the 3/2. 2 times a half is 1, leaving us with a power of 3. Good. More simplification. We have 1 copy of tangent in the numerator, 3 copies of tangent in the denominator. It's also useful to swap out secant with 1 over cosine. Having 2 copies of tangent in the bottom, we can call that cotangent. 2 copies of cotangent is cosine squared theta over sine squared theta. And do a little more algebra again. Cancel out cosines. And then break up sines. If we have 1 cosine over sine, we can call that cotangent. And if we have 1 over sine, we can call that cosecant. And this is an elementary integral. Negative cosecant theta plus any constant. And don't forget the constant out in front, 1/9. Very good. So we've found an antiderivative, and this antiderivative is expressed in the new variable theta. So now we want to return thetas back to x's. And we do that through our identification, x equals 3 secant theta. So what's that going to imply for cosecant? Well, if we know that x is 3 secant theta, then secant theta is x over 3. So secant of theta is x over 3. And then using this right triangle definition for secant theta, we can then produce the opposite as, by the Pythagorean theorem, the radical of x squared minus 9. And then use the right triangle definition for cosecant of theta to come up with x over the square root of x squared minus 9. Fantastic. Your turn. So evaluate. We have integrand. It's a radical term. Whenever you have a radical, that's always a tip-off to consider trig substitution. And do some algebra to clean up, to simplify the integrand so that you can match the variable squared minus a constant and use trigonometric substitution by swapping out x's for secants. Very nice. That finishes up this section on trigonometric substitution. Thank you so much for watching. Please like if you find this useful, and I will see you on the next one.